All right, folks, let's go ahead and get started. Welcome to the May Third Thursday Web Forum for the Southeast Conservation Adaptation Strategy, or SECAS. We host this web forum on the third Thursday of every month as an opportunity to share the latest updates about the blueprint, get input and involvement from folks like y'all, and highlight exciting science and success stories in the world of landscape conservation in the Southeast and Caribbean. So as always, I'll be your host today. I'm Hillary Morris, and I work on user support for the Southeast Blueprint, as well as communications for the SECAS partnership. So here's our agenda for today. I'll start out by introducing our speakers who will present for 30 to 40 minutes or so on our topic. There'll be time at the end for Q&A and discussion, and then I'll wrap up by previewing next month's webinar and sharing a couple of quick updates from your SECAS staff. As a heads up, you probably noticed we are recording this web forum just as an option for the couple of people who inevitably will reach out to me later and say, hey, I couldn't come, but I'd love to see the recording. I'll post the recording and a link to the slides from the event page of the SECAS website within a couple of days. Any questions or comments before we jump in today? All right, so without further ado, I'm going to introduce our speakers. We're going to be hearing from Dr. Michelle Moorman with the U.S. Fish and Wildlife Service. She's with the Southeast Inventory and Monitoring Branch, and Dr. Zafer Defne, who's an oceanographer with the U.S. Geological Survey based at Woods Hole Coastal and Marine Science Center. So their presentation is going to blend a lot of what we know about coastal marsh change in the Southeast, some of which y'all may have heard about on this web forum and past presentations. We'll be looking at surface elevation table monitoring across national wildlife refuges, more of a remote sensed perspective on how our salt marshes are changing, and input from coastal resource managers. So with that, I'm going to hand things off to Michelle to get us started.
Well, thanks everyone for giving us the opportunity to come and share this work. We are really excited to present today. So today's talk, we are going to give a brief overview of coastal wetland transformation, and then we're going to talk about ways we've been monitoring coastal wetland transformation using both surface elevation tables, as well as a remote sensing product called the unvegetated vegetated ratio. And then finally, we're going to dive into how we've been using this information to inform decision making. So briefly, ecological transformation can be defined as change that rearranges historical species composition and the ecological function of habitats. Coastal wetlands, as well documented in geologic history, do occur in a transgressive landscape where transformations between ecosystems are based on elevation and salinity gradients, with salt marshes occurring on the seaward end of the gradient and our forested wetlands on the upslope end of the gradient. So one of the great current debates in coastal ecology is how will sea level rise, which is currently accelerating, transform our coastal wetlands. And this is definitely a topic of concern to our coastal wetland managers because coastal wetlands provide important ecosystem services, including habitat for a variety of fish and wildlife species we've been entrusted to manage. But we cannot deny that our coastal wetlands are being transformed by sea level rise, storm surge, saltwater intrusion, erosion, and subsidence. And this is all altering the species composition and ecological function of these systems. We are seeing salt marsh convert to open water, and freshwater and forested wetlands convert to salt marsh.
Oh no, did we just lose Michelle?
Sorry, can you hear me now?
Yeah, you're back.
Okay.
I've lost your screen share though.
So as mentioning, and we see evidence of these transformations on the landscape, which, you know, with the recent increase in of sea level rise over the past 10 years, these changes are even happening at a faster rate. So starting in 2011, the National Wildlife Refuge System in the South Atlantic geography came together to discuss, you know, how we might monitor these coastal wetland transformations that managers were seeing on the landscape even then. And we decided to implement a monitoring program in 22 priority habitats across 20 national wildlife refuges in the South Atlantic. Monitoring sites were established in Allegheny marshes, salt marshes, forested wetland, and Pecosins across the South Atlantic. And at the time, the best available tool for monitoring coastal wetlands was the surface elevation table marker horizon technique. This is a technique that includes installing a benchmark in the wetland plane, and then you attach this surface elevation table instrument to it to measure the surface of the wetland through time. In addition, you can place a feldspar layer, which allows us to measure accretion through time. And the way that this works is that you measure wetland elevation change with the surface elevation table, and then you can tie that information back to a known wetland elevation surface by surveying the benchmark that you've installed into the marsh. And then this information can be compared with a local tide gauge, which is measuring the rate of sea level rise. In addition, these feldspar plots can be installed, which allow us to measure vertical accretion through time. And with this information, we can answer questions such as, what is the rate of wetland elevation change, and how do rates of wetland elevation change compare to rates of sea level rise? So after 10 years, we have some results. And in this graph, we are looking at the mean surface elevation trend in millimeters per year for each set site. So the x-axis shows each site color-coded by the priority habitat being monitored within each refuge. And the y-axis provides the set trend in millimeters per year. So each box plot shown here is the mean and standard deviation for each national wildlife refuge site, which includes 3 set benchmarks. The grayed area represents the long-term rate of sea level rise, which is less than the currently published 10-year rates. And what we see is that 85% of our wetlands across our national wildlife refuges that were being monitored as part of this study are not keeping pace with sea level rise. Additionally, it appeared to us when we first saw this data that rates of elevation change varied by wetland type. And when we look at the individual national wildlife refuge sites being monitored, we can also then compare how the mean elevation of the water, shown in blue, compares to the change in land surface, shown in level. So what we're looking at here on the x-axis is time. So all of our sites have 10 years of data dating back to 2011, and how this compares to the vertical datum in NAVD 88. So the sea level rise trends in this graph actually represent the true mean surface water elevations of the NOAA tide stations during this period. So they capture that accelerated rate of sea level rise we just looked at. And this is different from the long-term rates we saw on the previous slide. So a key take-home of this slide is that elevation capital, the height of the wetland plain above mean sea level, is really important because it is an estimate of the time until potential for submergence. So for example, even though the Pecosins at Alligator River and Pecosin Lakes National Wildlife Refuge are losing elevation, Pecosin Lakes has significantly more elevation capital than Alligator River, meaning that it has more time until submergence. So next we can ask, how do the rates of elevation change vary by habitat, to look at some regional insights. And so what we did here is we fit a generalized mixed effects linear model to test for the differences among our priority wetland types. And of the 4 coastal wetland types monitored, only our oligohaline wetlands within our study had a mean surface elevation trend greater than the corresponding rate of long-term sea level rise. And then if we consider the hydrology or geomorphic setting of the site, when we look at our oligohaline wetlands, we see that our tidally influenced freshwater sites, shown by the red squares, have the highest net elevation gains. So one of the management take-homes from this is that the conservation of oligohaline marshes is likely a good bet because they have the biophysical processes needed to maintain elevation and also represent a transition zone for marsh migration. We also note the forested wetland site at the mouth of the Roanoke River is slowly drowning due to sea level rise, and that the salt marsh sites have net elevation losses, which suggests that eventually our salt marshes will transgress to open water. So the take home here really is that we do need a plan for transgression, but we also might want to consider management actions to extend the life of our coastal wetlands in the near term, especially if they protect critical habitat for endangered species or important infrastructure. Now, what about the above and below ground processes that could be driving changes in our coastal wetlands? As we mentioned, we laid feldspar plots, which allow us to monitor vertical accretion and help us better understand why a site might be gaining or losing elevation. And so this graph here is showing us the difference between the accretion rates, shown in white, and the surface elevation trends, which provide an estimate of subsidence. This allows us to then categorize the subsurface processes that could potentially play in surface elevation gains by habitat type. And so as we see here, there was no measured accretion at Roanoke River or Poquoson Lakes National Wildlife Refuge, which means that there's no accretion happening on the marsh plain or in the wetland plain. And we attribute this to the fact that there's really no tidal fluctuations occurring at these sites. So there's no chance for sediment deposition in the near term. Conversely, if you look at our oligohaline marsh sites, which are getting flooded, you see that the tidally influenced sites, which are being flooded twice daily and after large storm surges, have high rates of accretion, with the highest rates being measured in the freshwater system of Waccamaw National Wildlife Refuge. You'll also note that the higher the rate of accretion, the higher estimate of subsidence for the site, suggesting that increased accretion is compacting the soil. So this is something to consider when considering treatments such as thin layer deposition. Conversely, the oligohaline sites in the Currituck suggest that increases in accretion and below ground biomass are occurring. We see less superficial accretion because these sites are not being flooded daily. But we do have some hypotheses to explain why the above ground biomass is higher. It could be due to the site's low elevation capital. It could also be due to prescribed burning, which has happened on this site, or the fact that its tidal regime. So now that we have all this information from our SET network, we also looked beyond our national wildlife boundaries and entered into some partnerships that have facilitated data sharing and information at the state, regional, and national level. And this has informed our understanding beyond national wildlife boundaries. This has to include an analysis for the state of North Carolina by the North Carolina SET Community of Practice, which found about 85% or 112 of the 132 sets being monitored in our site. The state were not keeping pace with sea level rise. And additionally, our work is being included in a national analysis that's being written up now and found that 344 out of the 411 sites in this data set are not keeping pace with sea level rise. So we have this set data, and it's all suggesting that the majority of our coastal wetlands are not keeping pace with sea level rise. But we realize at the same time, we need to understand what's going on with our coastal wetlands at sites not being monitored by SETs and at the landscape scale. And due to the improvements in satellite imagery as well as computing power, we now have some remote sensing tools that have allowed us to explore other techniques for understanding coastal wetland vulnerability. And one of these techniques is the unvegetated-vegetated ratio, which allows us to monitor marshes in tidally influenced wetlands. So I'm going to turn it over to Zafer right now to talk about a collaborative effort we've been working on with USGS to explore this information.
Thank you, Michelle. I'm sharing my presentation. It's loading. You should be seeing my presentation.
Yep, looks great.
Okay, thank you very much. And hi, everybody. I'm going to talk about applying geospatial metrics to guide monitoring and restoration in tidal wetlands. I'm filling in for Neil Ganja today. He is the principal investigation on our coastal wetlands research. I've been working with him from the beginning of our work on coastal wetlands. I developed geospatial methods. A few years ago, Kate Eckerman, our colleague also from our center, joined us to help with those. And we have Brady Couillon from Wetland Aquatic Research Center, who is in charge of the Landsat analysis. And recently, we have been collaborating with Michelle on how we can apply these metrics for management purposes and combining them with the vertical metrics coming from the SET data set. Just to put everything in a context, the geomorphic vulnerability of salt marshes can be grouped into three modes. First one is the edge erosion that happens on the open water side of the coastal marshes, and it's driven by the water, basically the wave and the currents, the erosive forces, and the geomorphology of the marsh coastline. Second one is the internal deterioration that takes in place within the marsh itself, actually, and it's due to different reasons, but they're all interrelated as well. It could be sediment deficits, herbivory, or salinity stress and sea level rise. But it's ultimately diagnosed through the conversion to open water and elevation loss within the marsh. The last one is the migration potential, or actually the lack of migration potential is another vulnerability. It's a function of the migration is a function of the inundation frequency, change in salinity, and the upland or the inland land use and canopy cover. So today the talk is mostly going to be about the internal deterioration. So in 2017 we did this study around across the 8 wetlands across the nation. We have been collecting sediment data at these creeks, and they were continuous sediment monitoring sites, collecting data every 15 minutes for several months and sometimes up to a year. And we wanted to establish a sediment budget and tie it to an independent metric. So then we defined these in order to do this, we defined these marsh units. They're sort of watersheds, and they're based on watershed analysis. They're like creek sheds behind the measurement section where the sediment budget can be put in a control volume, basically. And the idea was that if marsh is internally deteriorating, it's releasing sediment to the environment, and we should be observing that through the creeks. And that deterioration can be monitored through conversion to open water within the marsh. So we merged the on-site sediment measurements with geospatial analysis. Our geospatial analysis was based on the aerial imagery from National Agricultural Imaging Program, which is about 1 meter resolution, and defined this UVVR, which is the short for unvegetated to vegetated area ratio. We published a paper in 2017 and looked at this relation between these parameters. In this figure, you can see the net sediment budget on the y-axis and then the UVR on the x-axis, and there's a clear relation between the two. As the open water conversion increases or the unvegetated area increases, there is more export of sediment from the system, which is negative. So it's a sediment deficit. And you can see that there is around UVR equal to 0.1. There's a tipping point. And all of the sites that we looked at in that study were actually, they all had sediment deficits. Even though they seem to be more intact than another, or in worse shape than another, they all had sediment deficits. And in literature, other studies have also pointed out this tipping point being around this same number. And this is how it looks in the examples that we discussed about. This is Fishing Bay from Chesapeake Bay, which is more in more horizontally intact situation. This is Reedy Creek from Barnegat Bay, New Jersey, and this is the Blackwater from Chesapeake again. So today I'm going to talk about our land scale analysis and how we can tie those results to application management. First, I'm going to talk about the nature of our land scale data set. It's a 30-meter resolution data set. Every pixel shows the fractional vegetation cover and the UVR value calculated from that. So you have the ratio of the vegetated to the unvegetated area at every pixel. We have coverage for 5 years from 2014 to 2018, and we provide those annual data sets plus an average for that 5-year period. And the data can be accessed from the link here, and then the details of the methods can be found in the link below. So first is how can we compare this geospatial data set to vertical elevation gain? SETs are very powerful tools in terms of measuring the vertical change. They're precise measurements for that purpose, but by nature, by design, they are unaware of the horizontal disintegrity or the loss of integrity in the marshes. So this seemed to be a good opportunity to marry the two approaches, basically, where we can look in the horizontal deterioration and also the vertical change in the marsh platform. SETs are expensive to service and maintain, and sometimes data can be difficult to get, and it could be a little bit noisy. But the idea is to see if we could tie these two types of measurements together and get a more comprehensive idea about the status of the marsh. So for that, we worked with Michelle. We looked at 15 national wildlife refuges in the Southeast, where there set tables, SET data at each refuge. And the question there was whether these SET data were the set locations were representative of the entire marsh, and whether we could have a relation between vertical gain and horizontal integrity. So the answer to the first question, to answer that, we looked at different geospatial areas to see whether the UVR at the set location is coherent with the polygon that is bounded with the creeks and the and other constrictions. That's the red area here, or whether it's more coherent with the emergent wetland, vegetated wetland, which is the red and the green area here. And whether the tidal wetlands is a larger footprint, now we have the shallow water inundated parts of the wetland as well, or whether the refuge boundaries. So the overall, the UVR look at the set location, the UVR at the set location was a good representative of the good representation of the wetland itself, but the maximum correlation was for the emergent wetlands layer. So then how can we, the second question was, how can we relate the two measurements? So in this plot, we have the UVR on the x-axis and elevation matching on the y-axis, which could be an elevation or elevation change rate. So you can imagine for different combinations of these two parameters, we could have these four boxes of status The first one is where the elevation is high, or there is elevation gain, and UVVR is low, which means the vegetation is intact. There's horizontal integrity. This box number 1. Box number 2 is where you are still below the threshold, so you have horizontal integrity, but there's submergence because of the low elevation. The box number 3 is the worst case scenario. There's no horizontal integrity, and the elevation is low, so it's coherent deterioration. And box number 4 is a mix where there's vegetation loss, but we're also observing net vertical gain. So when we plot our data in this fashion, it's the same concept. Now the boxes are a little squeezed out because we had to expand the UVR coverage because it goes to larger numbers. So again, in that study, we had salt marshes and oligohaline marshes. In general, the oligohaline marshes were keeping up with the sea level rise. The elevation metric on this y-axis and this plot is now elevation change as adjusted to the sea level rise. So we are looking at the additional elevation change when we take out the sea level rise from the elevation capital. Also, no site above the threshold UV value were able to keep up with the sea level rise. And no salt marshes with the in Georgia or South Carolina with UV lower than the threshold were able to keep up with the sea level rise either. So there's something that we have seen in general when we look at the Landsat results, that there might be a connection between the sparse vegetated plains and low rates of accretion and biomass in the South Carolina and Georgia marshes. So another interesting thing is we don't have any example for box number 4 from the previous image. But that's not always the case. Another study, recent study from Louisiana, showed that actually the dominant mode of this relationship was box number 4, where there is net vertical gain with horizontal deterioration. Those are the red points shown here, mostly lateral erosion, but also vertical gain. And that same study alluded that the rapid elevation gain actually could be a warning sign of rapid increase in UVR and actually deterioration. So the idea is, how can we tie these models to external forcing, biochemical process, or anthropogenic actions, and how do marshes move from box number 1, where there's coherent stability, which path do they follow in terms of the trajectory of deterioration? And again, once we plot the data in this fashion for management purposes, maybe box number 1 is where these marshes should be protected because there's coherent stability in those marshes. And box number 2 is horizontally intact, but there is submergence, so maybe they need to be monitored. And maybe in terms of putting restoration efforts in, box number 4 is a better target. And box number 3, although it's coherent deterioration, maybe we should just let it go, do nothing, unless that marsh is protecting some structure behind it. So we can also, one may guess, we can also track the change in vegetative cover in time, because we have that temporal coverage. We can track the restoration efforts and the dieback in the satellite imagery. These are examples from Prime Hook, Bayou Savage, and Everglades. So in Prime Hook, there was aerial seeding and restoration, and we can see the net gain of area in our geospatial results, which matches with on-site analysis of the areas. Bayou again has the Turtle Bayou and Bayou Chevet, where there has been restoration projects, and those can be captured here as well. So the percent vegetated cover is increasing there. And also in Everglades, due to Hurricane Irma in 2017, there was an extensive dieback on mangrove, and that also can be seen as change from 100% coverage shown in blue in the figures to less vegetated cover. So how can we map vulnerability using this data set? Here's another way to look at the UVR data set. Now, we're only plotting UVR here. Y-axis is not elevation. Y-axis is the standard deviation in the UVR. So the way we do this, we do this is we plot the average for 5-year composite, 2014 to 2018, an average value for 5 years on x-axis, and then the variation in those values in all 5 data points for that time period is the standard deviation on the y-axis. So one may guess if the standard deviation is smaller, that means there is a consistent results throughout the years. So there is low uncertainty. That will be the boxes 1 and 4, where we have low uncertainty, and based on the UVR threshold, we can say, yes, this part of the marsh is stable, and we are more certain about it because the 5-year data gave similar results. Again, those points and the plot are pixels from each pixel for this marsh, which is Mackay Island. And of course, then we can plot this on the map, which is the panel on the right here. Then you have a clear idea of where the marsh seems to be more stable and where we have more certainty about it. And here, I don't know if you can see, but the light pink color are the areas where there is a regular inundation. So the results are variable in that, and they're unstable, but there is higher uncertainty. But the darker pink color are unstable, and we are more certain about that the conditions are worse in there. And something that is coming up is now that we have this 5-year data set, and we can look in the change in time, we can also do surveillance of marshes through time, because the Landsat data actually covers from 1984 to today. And recently we started analyzing that data set. And these are some preliminary results for the places that I have talked about before. This is the Bayou Savage with Turtle Bayou and the other restoration area shown in red and blue from 1984 and 2023. We see 2 snapshots here, and might be a little difficult to see in the figure, but we can actually aggregate the pixels to get an overall idea about those areas within those polygons, and that's how it looks. The restoration efforts start after 2016, and we can see a clear signal of increase in vegetative fraction. So with that, I conclude my presentation, and back at you, Michelle.
Yeah, thanks, Zafer. Appreciate that. So with both of these monitoring data sets, we had a couple take-homes. One was that the SET and UVVR data are well correlated, and both data sets help to provide information on wetland vulnerability and site-specific information on wetland vulnerability and restoration response. Secondly, the SET data suggests current day marshes cannot keep pace with accelerated sea level rise and provide insight on site-specific above and below ground processes driving wetland change at the site. And then finally, the UVVR provides a spatial assessment of wetland stability and vegetation change across the wetland plain that can be used to assess restoration success and plan for climate adaptation. So now that we had these results, we wanted to think about how we might share this data with our managers across the Southeast. And so we had the idea to develop an online mapping tool that would include both the SET and UVVR data for Southeast National Wildlife Refuges. But we wanted to co-produce this online mapping tool with our refuge managers and staff to make sure, one, that our results could be ground truth by them and learn insight from them about what they're seeing on the ground as how it related to this data. Second, to provide training on the data and the tool. And third, to improve our understanding of how this monitoring data could be made in decision-making and tell that story through various story maps for our case studies. So real quickly, Hillary can provide the links, but I want to go through what these tools look like with the hopes that you guys might go explore them yourself. So the USGS has this coastal wetland synthesis application page, and they've put a geonarrative together for the Southeast region application, which you can access on the Southeast Refuges tab. And if you want to go to the application itself, you can click on the Southeast region application and then open the application in a separate window, which takes you to something that looks like this. If you are interested in a specific National Wildlife Refuge, you can go to the Bookmarks tab and click on that refuge, and then go and look at the specific data for that refuge, in this case, Waccamaw National Wildlife Refuge. And there's a legend which shows you how to interpret the, so you could get specific metrics for the refuge on the UVVR vegetation change, as well as specific metrics on the SET data. And so you can link to the application and explore it on your own. In addition, as I mentioned, we're working on developing story maps to show how managers are using this information in decision making. And one of these story maps for Waccamaw National Wildlife Refuge has been completed. So you can go check that out for yourself. And the take home was that our managers and staff really found this information useful, and it found that it allowed them to assess wetland vulnerability, make RAD decisions, and evaluate restoration success. And an overall theme we heard from managers is that we now have the science we need to support what we are seeing on the ground. Now, I just mentioned RAD decisions, which, although a cool acronym, RAD stands for the Resist, Accept, Direct framework, which is really a framework for thinking about how we might manage through ecological transformation. Really comes down to thinking about what is the management intervention you're thinking about doing. So accept interventions are interventions where you allow ecological transformation to happen without intervention, whereas resist interventions are interventions designed to conserve the habitat in the state it's in, whereas direct interventions are to plan forward, realizing that ecological transformations are happening. And so we thought it might be useful to show how the UVVR and SET data might be used to come up with, facilitate some RAD management decisions. All right, for instance, this information could be used to determine where to resist marsh loss and identify vulnerable marshes that should be prioritized for restoration activities because they protect critical habitat or infrastructure. So example of this would be at Mackay Island, where the SET is not keeping pace with the sea level rise as shown by the light blue dot. And in the same location, vegetation is unstable according to the UVVR. And so this might be an appropriate spot for restoration because this is where a road is located, and thus the loss of the marsh threatens the loss of important infrastructure. Alternatively, at sites like Currituck National Wildlife Refuge, where marshes and SET data suggest the marsh is relatively stable, we'll let the marsh be and continue to monitor. An example of an accept action might be to accept potential loss of marsh in areas designated a wilderness area because the policy precludes us from going in and conducting active management. And here we can see the set data indicates that the vertical accretion is not keeping pace with sea level rise, as well as we have a lot of interior ponding that's showing up in the UVVR and also showing up on the landscape when we go out to monitor sets. Another example of an accept action is that lots of our managers are accepting coastal wetland transgression is occurring on the landscape, as evidenced by ghost forest and receding shorelines. And so they are planning to acquire migration spaces through either major or minor boundary expansions or the acquisition of upslope lands, such as the recent purchase by Cape Romaine National Wildlife Refuge. And then finally, an example of a direct action is that black rail, which is a species that depends on high marsh habitat and is losing that habitat to sea level rise. We are now looking at converting inland impoundments into freshwater marshes that are suitable for black rail to provide this lost habitat to the black rails inland as the high marsh habitat is lost. So in conclusion, our set data suggests that 85% of coastal wetlands are not keeping pace with sea level rise and thus vulnerable to ecological transformation in the coming decades. We also see that set and UVVR data are well correlated and thus are both appropriate metrics for understanding wetland vulnerability, and that the set UVR mapper provides site-specific evidence on coastal wetland vulnerability and thus can inform planning and decision-making by providing this information in a way that's easy to access by managers. And then moving forward, we hope to include additional UVVR time steps into this mapper. So with that, I just want to acknowledge that we covered a lot in our presentation today, and this work would not be possible without the contributions of many. And here is my contact information. So if anybody has any ideas or input or goes and checks out the mapper and has suggestions for improvement, we would gladly hear that. I'm also providing some additional resources, including the published paper that summarizes the results from our set monitoring we presented today, results from the set UVVR paper, information from that North Carolina set community of practice analysis, and links to the various mapping tools that were shared. So with that, I'm happy to take any questions.
Thank you so much, Michelle and Zafer. That was fantastic and super comprehensive presentation. So I've had a couple of questions in the chat from Woody Woodrow, and Woody, you are welcome to pop yourself off of mute and speak up and ask your questions if you want that you put in the chat.
Yeah, sure. On Defne's on one of your slides that you had an image showing where what the set station was, and it was all red, and then you had these other polygons in the map that were sort of green. And the label was like, you had one label said tidal wetlands, and then the other one said emergent wetlands. And are the emergent wetlands the oligohaline wetlands? Because I mean, tidal wetlands and emergent wetlands, they would both be emergent wetlands, right?
Yeah, I can answer that question. The classification comes from the National Wetland Inventory's classification. So emergent means where there is vegetation, it's emergent vegetation. And the oligohaline or tidal, the salt regime is a different identified in that database. So vegetated area can be oligohaline, freshwater, or saltwater. When we say tidal wetlands, they have these modifiers in their database. So again, a tidal wetland could be a freshwater tidal wetland or a saltwater tidal wetland. It's a general classification based on those modifiers. So I think the answer to your question is emergent can be oligohaline or saltwater marsh.
Yeah, no, I mean I understand that, but in the map it didn't. I couldn't tell what the difference was between the red and the, I guess maybe the green, because they're both could be emergent. You know, one says emergent, the other one says tidal. So I'm just curious, like what how does that?
I can try to explain more. I don't know if it's going to be helpful without.
That's okay. If you could show the map, then that would help a lot. If you show that slide.
Okay, yeah, sure. Yep.
Because I mean, it just maybe it's just a choice of the legend or something. But anyways, and then the other question I have is, so I really liked the great work, by the way. Thank you very much. It's a lot of stuff going on in my head. Your the graph that showed the table where you had like your salt marsh, everything that was higher salinities than oligohaline, and then your oligohaline, the blue dots and the red dots. So could you? So one question I guess I have is I would expect oligohaline marshes to have a better track record of keeping up with sea level rise because they are accumulating organic material, right? Yeah, that slide. So
yeah, let me start with this slide. So the red one is a polygon basically bounded by the geography. It could be the tidal creeks or a road constriction, etc. So it's where we can pull out that polygon from the map. So it is actually I don't know if I start this slide again, it's actually, well, it doesn't help, but that green actually includes red as well.
Into the red?
Right.
Yeah.
Because they're plotted on top of each other.
And then is the blue actually open water, or is it?
That again is the tidal wetlands. So that modifier that they have in the database for tidal wetlands, it could go to any of those emergent, scrub shrub.
Yeah, sure. So then, what is the emergent then in terms of salinity? On the yeah.
At this site, it's oligohaline. So we actually this is the various ways that we compared the set data with all these different levels of polygons. I think that's the purpose of this slide. But we actually measured salinity at all our sites, and so this site falls under 5 parts per 1,000, and thus is classified as oligohaline.
Yeah. So, but that helps a lot. Because it just says emergent, and that doesn't really tell me a lot. So getting back to the oligohaline versus the tidal, like that's great. I would expect that your blues are keeping up because they're going to have more organic accretion, right?
They are, yeah. In general, they are doing better than salt marshes, correct?
Right. So, but then what happens is eventually, over time, those will they'll experience more higher saline events. And they'll transition to down it below the line because you're going to lose all your carbon is going to be exported out of the system.
Correct.
And so one thing I guess, have you all had conversations about sediment supplementation? So like putting mineral sediments into these systems to help recover their elevations? Like use dredge material, direct dredging, to help those tidal marshes sort of help them along, at least keep pace, a little pace.
Yeah, I think that's kind of, so as scientists, we're providing this information to the managers, but I know, for instance, at Cape Remain, they're coordinating with the Corps at potentially applying some dredge sediments onto, I think it's Monkey Island, but one of the islands down there. So that is like a conversation that's happening. As we also saw from the data, the freshwater sites, right? The higher the rates of accretion, the more shallow subsidence you might have. And there's other examples of places where they've put down thin layer deposition. So that's definitely something to keep in mind. But I know that managers themselves are working on thinking about where they could potentially use thin layer placement to enhance elevation, right? So the take home is we aren't keeping up with sea level rise. And so hopefully these tools can help them think a little bit more about where they might strategically do that, because we can't apply thin layer deposition everywhere, right? There's not enough sediment. So, yeah.
Well, there's lots of dirt. It's just very costly to move it.
Yeah.
The Matt Whitbeck is a good person. We're at Blackwater to then thin layer deposition. There, it's pretty good approach. So no, thank you very much. This is a very good topic, and appreciate it.
Thank you.
Appreciate that question. Doug Newcomb, I see your hand. We've got a couple more minutes, so I might make this the last question, depending on how long this takes.
It's fair. Have you looked at the possibility of doing a bathtub style inundation of the sea level rise models and comparing that, say, going back to 2000 with the 2017 model stepwise, and seeing if you can pull out that signal of transformation by the different model steps for a large area?
I think it was a question for me.
Yes.
No, I haven't done that. No, we're using the sea level rise data from the NOAA's Sweet et al. Sea level rise data. We have done something similar. We also calculate lifespan based on the sea level rise and UVVR. That's something that we tried in there. Neil was looking at it. And I don't have any answer to that at the moment, but please follow up and we can chat.
I've got some data along that way that you might be interested in.
That'd be great. Thank you very much, Doug.
Awesome. I might take one more if there's anybody else with a burning question before I wrap things up. Larry, I see your hand. Larry, you're welcome to pop off mute and speak up if you want. I see your hand.
Great. Yeah, I can do that. Right. Thank you. I wanted to ask about subsidence. You mentioned it once at the beginning that it is included into the general foray of all of the causes, and that particularly when you measure it at the SET. So when you're talking to managers, though, is it possible to pull subsidence data out separate for all of these sites into the UVV so that the managers would know what sites are simply in your 4 squares? Subsidences can be a major directive in like number 3 and number 4, and even partially in the number 2. So to tell your managers the aspect of subsidence, and because I'm sure they all know, well, hey, is this another one of those, should we give up on? Because the subsidence is so great. We can't do anything about the subsidence. The accretion may be there, but the accretion is not keeping up. And that.
That's a very good point, Larry. I'm sorry, Michelle. I was just gonna thank for that idea. I think it's a very good idea and good point.
So also to get at that, Larry, so there's deep subsidence and shallow subsidence. They're 2 separate things. So that's one of those things where the set data, right, provides more of the information about the above and below ground processes. So we captured the deep subsidence with the sea level rise data because it's relative sea level rise data. We can also actually use the benchmarks that are out there if we go out and take repeated measurements with the RTK to get an idea of local deep subsidence. So that's something we haven't done yet, but are anticipating tackling in the future. And then that shallow subsidence rate is then captured by the accretion measurements in what's estimated. So you do need like that information. That's one of the values of the set, is it gives us a little bit more insight into those site specific processes.
Thank you.
Thanks, Larry. Well, in the last 2 minutes, I'm going to wrap up just by giving a quick preview of next month's web forum. Huge thanks to Michelle and Zafer for that fantastic presentation. Making sure I'm sharing my screen here. So next month, same time, same connection information as today. It'll be a June 20th date. We're going to be hearing from Lauren Berry, who's a master's student at the University of Arkansas, and Caleb Roberts, who's the unit leader for the Arkansas Cooperative Fish and Wildlife Research Unit. And they're going to be talking about tools to identify intact grasslands and track restoration outcomes. We know that grasslands are rapidly losing biodiversity. Woody plant encroachment is one of the major drivers of that. And so there's a desire to identify the remaining core grasslands and track how well restoration actions are working, which can often be tough because we don't necessarily have all the tools we need to map and track these core grassland habitats and how their biodiversity responds to management. So they're going to be talking about some metrics and some projects related to greater prairie chicken and other grassland bird communities, how they've responded to prescribed fire in tall grass prairies and grasslands and savannas in Arkansas. So definitely excited for that talk. I wanted to provide a quick sneak peek of our SECAS logo as our staff update. We have finally developed a logo for SECAS, and it's going to be unveiled very soon, along with a branding guide to go along with it. So that's what that looks like. And then since we're at time, I'm just going to finish with my usual last slide, how to get more involved in SECAS. I encourage you to join the SECAS newsletter, which you can do on the footer of any page of the SECAS website. That'll get you signed up for our monthly newsletter, as well as a monthly reminder email about this web forum. You're welcome to connect with your SECAS staff. We encourage you to explore the blueprint, which is using this great UVVR data that Zafer talked about as one of our indicators of stable coastal wetlands. And so I encourage you to check that out. Reach out if you need help and let us know how it's working for you. So with that, we're at 11. So I'm going to go ahead and say that we end for today. But again, thank you so much to Zafer and Michelle and to all of you all for tuning in. I hope we'll see you again in June.